Yeah. I think so. Yeah. I think my favorite word was sound modeling. Oh, yeah. Those guys, we got Stefano and
yeah, very, very nice. Well, their products, they're good too. Sounds, the tenor, really, really amazing. So.
Oh.
I'm going to just play with
Now we got to
Yeah,
that's what I'm using. It's like the ice resistance.
Oh, okay.
but I haven't had time
Very
to
raising.
Yeah, no, I talked to them for like 15 minutes, and they were very nice.
Yeah, it's super nice.
How have you been?
Stefano was doing well. I used Stefano was
Oh yeah, sure.
I don't know what it is. I always have a rule. I'm 6 weeks fine for a week. I'm not used to that weather.
I think that's it. Yeah, everything is way too fine. The body's rejecting it.
Or maybe just work with your No, probably. Of course not. No, exactly. But today I thought it really well, so I'm enjoying it.
Hi everyone. Today we have Peter Svensson from Trondheim in Norway, and he's going to talk about room acoustics. Enjoy the talk, and if you didn't grab food, there is food in the back of the room, of course.
Okay, thank you very much for the introduction, and thank you, Julius and others, for inviting me here and to give a speech here. So I will talk about room acoustic conditions for a special case of rooms, for video conferencing. I will start with the usual thanks to the people that have actually done the work. Colleagues at NTNU, a PhD student, Hassan Siran, Ulrich Reiter, postdoc, Ellen Gundersen, a master student, and also some colleagues at SINTEF have been involved, and SINTEF is a contract research institute in Norway, a bit like Fraunhofer in Germany, which you might be familiar with. And finally, Johan Nielsen at Cisco in Oslo. They have been involved in a research project together with us, and it used to be Tandberg in Oslo that were acquired by Cisco a few years ago. So the Norwegian Research Council and Statoil and Cisco, earlier Tandberg, were funding a project where Hassan Siran worked. And I might, I don't know, maybe I will disappoint you a little bit by mentioning that I will not talk about another part of this project, which was about spherical microphone arrays. That can be for another day, perhaps. Video is a company that gave access to a number of rooms for video conferencing. And finally, Silicon Valley Community Foundation that funded a part of this work for Ulrich Reiter. Okay, so I will talk quite a bit about classical room acoustics, and I will try to make a point about that the video conference situation gives us quite new conditions compared to classical room acoustics, because we have two rooms involved rather than one. I will start with a review of classical diffuse field models of the sound in a single room, which you might or might not be completely familiar with, and then use those for the convolution of two room impulse responses. A short discussion about what then happens in practice, what is the result of this theory for video conference rooms, and finally a slightly separate aspect, and that is, do we need binaural, to take into account binaural aspects for measures for speech in rooms? So first, I think there's something like 12 slides or so where I will go through the classical single room acoustics. So it's like room acoustics 101 if you want. So most is probably well known. Thanks to Sabine, we have these basic equations giving us the reverberation time, the absorption area in the room, and this expression for the sound pressure level as function of distance, including a direct sound and reverberation. No more detail than that, but it's still very useful. A room acoustic consultant can do quite much work based on only these three equations. I think we can admit. Since we are studying or going to talk about video conferencing rooms that have electroacoustic systems, we need to, in particular, involve the directivity factors, both of the source, which could be a loudspeaker or a speaking person, and the directivity factor of the receiver, which could be a listener or a microphone. And a little interesting detail about the reverberation level. The classical expression for the reverberation level in a room is that it's a simple constant, which means that the sound pressure level as a function of distance in a room will go towards a constant value. There's a slightly different value that some use, but a more substantial change was suggested by Baron in '88, where he suggested a factor which predicts that the reverberation level decreases with distance in the room. And that can indeed be observed in most rooms. And here, delta is a more compact way of writing, or a practical way of writing the reverberation time. So these things are things that we can figure out if we have nothing but a sound level meter, more or less, but we are interested in impulse response modeling. So that simple model can directly be represented by this simple room impulse response model, which has two parts: direct sound, which is a pulse, a single Dirac pulse, which is delayed by the distance given by which is delayed by a number of samples, which is given by the distance between source and receiver, and the reverberation, which is just the Gaussian noise sequence multiplied with an exponential window. This reverberation tail will naturally have to start after the direct sound, and it turns out that by having a constant amplitude here and by choosing that correctly, we will indeed get the Baron's model automatically for the reverberation level scaling. So, a few comments. This is certainly a very, very simple model. We are ignoring many things, but it's still very, very useful for doing many studies, to do a kind of the first level study of many aspects. Some of you might have worked with the image source method that Allen and Berkeley described for modeling a room, and this is very, very different, as it seems. They suggested a model where we have a number of distinct pulses with an increasing density. Here we have nothing like that. We have just a noise sequence which is decreasing exponentially. And one of the more important limitations here is probably that we are missing distinct early reflections. Also, as you can see, when we have a single such exponential window, we get the same reverberation time for all frequencies as it stands. And that leads to that we get a bit unnatural sound. So I will play a very, very simple sound example. This will actually be my only sound example, and it's very basic. And you will hear first an almost anechoic speech sample. That's something I recorded on my own laptop a while ago. Let's see, there.
Acoustics.
And then convolve with such an impulse response.
Acoustics.
I chose this specific sound sample for sentimental reasons. I recorded this in the winter of 2003 when Tom Rossing invited me to give a lecture on room acoustics at St. Olaf College. And and what was very funny then was that when I gave this presentation and I played these sound examples, then Tom pointed out that it's kind of funny that the amplifier seems to add a Scandinavian accent to the speech sample. So I think that could be a challenge for you at CCRMA to generate such an audio or speech processing filter that adds a Scandinavian accent to speech sample. Tom Rossing had such an amplifier at St. Olaf College. So back to the impulse response. The impulse response includes random variations because we use a random Gaussian sequence as a carrier with exponential envelope. Since we are synthesizing these, we can just plot the envelope, and we see that it does indeed have the direct sound and the linear decay on a logarithmic scale or on a dB scale. And we will see, I will come back to this a little bit later, so we see anyway that we have indeed exponential decay. Now, the next part of this will be about how we can analyze an impulse response and say something about how a room works for speech transmission. And there are, I will show 3 parameters here. There are others, for instance, the articulation index I don't include here. But you might know the clarity index, C50, which I will explain or show the definition of. And one which is a little bit better, called the useful to detrimental ratio, U50, and the most advanced one, the speech transmission index. So the C50, the clarity index, is like a signal to noise ratio, which is measured in decibels, which claims or is based on assuming that all the energy in the impulse response that arrives within 50 milliseconds is good, and everything that arrives after 50 milliseconds is bad. So this is signal and noise. And that division would perhaps be somewhere here in this example of an impulse response. There have certainly been arguments against this measure, because it seems ridiculous that a sound wave that arrives at 49.9 milliseconds is good, but if it arrives at 50.1 milliseconds, it's bad. But it turns out that in reality, it's not a problem, because there's practically never such an extreme situation. The slightly better measure is the useful to detrimental ratio, U50, which was suggested by John Bradley at NRC in Ottawa. That includes the background noise in the denominator. And that's a good idea, because if we have just the clarity index, this would mean that if we had an anechoic room which is 10 kilometers big, and we had a 10 kilometer distance between source and receiver, if we measure the impulse response, we had only a direct sound, the clarity index would be infinite, but we couldn't hear a person in 10 kilometers distance, because there's background noise in a room and there's our threshold of hearing, which acts as a background noise. One little showstopper with this is that if you want to take this into account, then you have to be really careful with the scaling of your measured impulse response. And finally, the most refined one, the speech transmission index. It is calculated or computed from the normalized modulation transfer function, which we get by taking a Fourier transform of the squared impulse response. And then we read that off for the modulation frequencies starting at 0.63 hertz, going up to 12.5 hertz, which is supposed to represent speech, the variation in speech signals. So we can see that this is clearly much more advanced, and the foundations seem to be much more reasonable than the very simple approaches here. But John Bradley, he has made a point about this, saying that the correlation between the speech transmission index and the U80, he happens to favor 80 milliseconds instead of 50 milliseconds for the division between early and late energy. And he points out that if the correlation between those two measures is like this in most practical rooms, and this is an advanced measure and this is a simple measure, why can't we use this? And it turns out that the correlation between this measure and actual speech intelligibility is on the same order as the STI. So that's good. We have used that because that makes it relevant to study the simpler measure of U80. Even though we are still sticking primarily to the 50 millisecond division, which most seem to favor for speech. Okay, so C50, even if we ignore background noise, C50 is a simple but very useful indicator for speech intelligibility in a room. But then, if we look at that a bit further, it turns out that C50 is also very closely related to the reverberation time. So Sabine kind of wins again in the end. This is simulated values for an example room. The C50 as a function of the reverberation time, if we vary the reverberation time, and we study just 3 different distances between the source and receiver, we see that there is certainly a small difference, but the absolutely largest variation in C50 is explained by the reverberation time. So, we have to take a step back perhaps and acknowledge that it's easy to be carried away when you see nice figures or curves like this that are based on a simple model. We have to remind ourselves every now and then that these are simple models of reality. If we measure, there will be a scatter around these, as here for instance. But nevertheless, C50 depends strongly on the reverberation time in classical single rooms acoustics. And by the way, the expression for C50 will look like this. There will be a direct sound term, the reverberation split up into the early part and the late part. So, this was the end of the single room acoustics, room acoustics 101. Then we take the step to room acoustics 102, next course. So what is the difference between our video conference situation and a case which is well known, which is coupled rooms? Coupled rooms we can read about in any book on room acoustics. That's when we have a connection, for instance, an opening between 2 parts of a room. If we have a source and the receiver in 2 different parts, we can set up those diffuse field models for such a situation when there is an interaction or exchange of energy. But here, we are claiming that we can study just a one-way transmission, thanks to all those people that do fantastic work with echo cancellation. Because echo cancellation is suppressing very efficiently the path that goes back and would feed back. So, so we are studying this path from the source to a receiver. And by the way, if we illustrate that like this, that we have 2 rooms, the sound is picked up by a microphone in the first room, in the sender room, and it's played back by a loudspeaker in the second room. So anyone listening to a recording of this would actually be in that situation. Now what is interesting is that if we use this simple diffuse field model, which has a direct sound, pulse, and an exponential decay, then we can treat those 2 components and convolve them with pairwise, and we get 1 direct sound, which is the first one convolved with the other one, direct sound. We get 2 exponential reverberation tails, this direct sound convolved with that reverberation, and vice versa. And the last part, which is a convolution of 2 exponential tails, which will generate a non-exponential reverberation decay. And if we look at the expected value, if we remove the random variations, the expected value of the squared impulse response, we will indeed see the pulse, 1 exponential decay with delta 1, another exponential decay with delta 2, and a last part which can be written as a difference between those 2 decays, but this forms a non-exponential decay. Now it will be so that this non-exponential part can be ignored, and correspondingly the direct sound will be more important. If, for instance, the microphone is very close to the mouth, so like in this situation, if this would be a video conferencing, we could largely ignore this room, or the reverberation would be quite weak. or if we had a microphone at a distance, but the microphone is very directional, or the listener sitting watching a recording. If the listener is wearing headphones, then there is no second room, or sits very close to speakers. But in many typical video conferencing situations, people don't want to wear a microphone, people don't want to wear headphones, obviously, so there can be this component can be more of an issue, or will be more of an issue. So a simple example, if we have two rooms, we just arbitrarily choose two different reverberation times, but we simulate or we show the result for two quite different situations. First, if we use short distances, both in the sender room and the receiver room, and we use directional microphone, loudspeaker, then we can indeed see that the direct sound is dominating. We can see a little bit of the non-exponential shape, but it's not too far from exponential decay. On the other hand, if there are longer distances, if the microphone is lying on the table, if it's an omnidirectional microphone, then we see that the direct sound is much less significant compared to the rest. And we can also see very clearly the non-exponential shape of especially of the early part of the decay. And we can perhaps already see or realize that this is actually a bit bad for this transmission of speech, because this early part is what is useful for the speech transmission. So when it has this shape, we are kind of pushing energy back towards later times when it's detrimental rather than useful. So that was about the theory. Then we can look at some measurements. So Erland Gundersen made measurements in 11 rooms that are actually used for video conferencing. And he calculated the early decay time, which is slightly different than the reverberation time, T60, but not too much. It would typically be a bit lower than the reverberation time, T60. And one can observe that these 11 rooms have a distribution of reverberation time and C50. There's one room that one can wonder how on earth they choose to use that for video conferencing. It has a long reverberation time, 0.9 seconds. Most of them are very dry, 0.2 to 0.3 seconds, and some intermediate values. We can also see that predicted values, according to this model, give values that are reasonably close to the measurements. And that these simplified predictions are lower, that probably is caused by that there are probably significant early reflections in the rooms that give a little bit higher early energy than according to this simple model. Then, Erland Gundersen, he simulated, as a first step, he has more data that I'm not going to show, but he did one simple step, and that is taking an impulse response measured in such a room and convolved it with itself, which is kind of a simulation of a video conferencing setup between two identical rooms. What happens then is that for all of these 11 dots, we get a new dot. So this one, convolved with itself, generates this point here. These generate the points here. Those three generate those values down there. And we can see that there's a clear kind of movement of those values. And on average, the C50, for these 11 cases, the C50 is lowered by 7 decibels, and the reverberation time is prolonged by 56% compared to the single room. So we get clearly worse conditions by connecting two identical rooms. So if we try to use our classical knowledge about single room acoustics, and we look at one room and we say that this seems to be okay for speech, then when we connect two together, we can get quite substantially worse conditions. To counteract that, one would need to apparently specify the reverberation time to be on the short end. one would need to be sure to try to use short distances if possible, and directional microphones to reduce this effect as much as possible. It's an interesting challenge that to decide or specify the room acoustical requirements for a video conferencing room is a bit trickier than the classical single room case. First, because there are more degrees of freedom. There's the microphone and loudspeaker distance, there's the microphone directivity, which means more degrees of freedom. So that means that there will not, for instance, be such a clear connection between reverberation time and this C50 clarity index. If a room is purpose-built for video conferencing, then certainly the designer can have control over these parameters. But very, very often, still, video conferencing systems are installed in a room that was available, or a room that was specified for something else, as an office, a meeting room, or whatever. And it mostly boils down to that the reverberation time is typically too long. This trickiness can also be expressed in this way. A video conference room needs to play 3 roles at the same time. It's a meeting room because there are people sitting together, and the conditions need to be pleasant for or suitable for a meeting room. It should also be a recording room because there's a microphone picking up the sound, and it should be a sound reproduction room. Sound will be played back over loudspeakers. It's always more challenging to design multi-purpose rooms, and here the main challenge is probably that a meeting room we would like to have a meeting room to have slightly longer reverberation time than those 2 others, for it to be pleasant to have a speech conversation in. We did, or Hassan Sidan, I should say, did a parameter study using this model by doing some variations. And I'm sorry if these diagrams are have a bit many details, but it shows, again, since we have focused on the relationship between the C50 clarity index and the reverberation time. First, the diagrams show, or this diagram shows curves that are valid for a single room and curves that are valid for 2 convolved rooms. And the 3 curves show maximum values, median values, and minimum values for the situation that this simulation, for each value of reverberation time, a number of source receiver distances have been tried out. Then you get a distribution of results, and a way to try to illustrate that is to show the maximum value that was found and the median value and minimum value. And we can again see that if we have, for instance, a room with 0.6 seconds reverberation time, we typically get C50 values up here, but we get a reduction when we connect those 2 rooms together by on the order of 5 to 6 decibels even here.
These are still pairs of identical rooms.
Yes, yes. Then a separate parameter variation was done here. What if we change the directivity index for the microphone and look at the C50, choosing a constant reverberation time, in the same reverberation time in both rooms, and adjust this. And I don't know how familiar you are with directivity indices for microphones, but an omnidirectional microphone is at 0 decibels. A cardioid microphone, a figure-of-8 microphone, is at 5 decibels. To reach values up to 10 decibels and even higher, you need quite an expensive advanced microphone. So this is quite a large range of values. But we can see that we get an almost frustratingly small variation here in C50. But reverberation time has quite an impact. So again, Sabine is, we shouldn't forget Sabine. Reverberation time does not tell everything about the room acoustical quality, but it tells a great deal, or it affects a great deal of things. Yeah.
How did you incorporate the microphone directivity in the model of the software?
It's involved. I have to go back to the first slide. Sorry. So our impulse response has a direct sound. I don't show it here, but the amplitude is corresponding to this amplitude here, the directivity factor of the source and of the receiver. And then if we have two rooms, we convolve two such impulse responses, so we get the directivity factor of the source in one room times etc. So does that seem
okay? Okay, so the directivity just lowers the reverb and the direct sound, basically, or the relative.
The relative difference. It depends on how you define your impulse response, but we have done it so that the reverberation level is not changed, but rather the direct sound is increased. It could be done the other way around, actually, depending on how you want to define your impulse response. So let's see. And now the last little part about this is about binaural aspects. I don't know if you if that struck you at all during this first part, but all the discussion until now has been on what we could call monaural aspects. It's what we can see in an impulse response that we measure with a single omnidirectional microphone. And that is what acousticians do, because we basically have only monaural room acoustical parameters for speech. For music, we have what is called the spatial impression aspects, which is considered to be important for music, but for speech we don't have that. So we are focusing on the temporal dependence, but we are ignoring the spatial dependence, and for that matter, the spectral, any spectral dependence. The STI is based on the monaural impulse response. Then we can ask ourselves, aren't we missing an important point? Because we know that there is something called the binaural advantage when listening to competing sounds, a source, a decided signal, and a disturbing signal, a noise. So we can, for instance, look at, take some examples from the literature. This paper in JASA from 2010 had a setup which has been used in many such studies. There's a target, which is playing speech, and there's an interferer, another loudspeaker, which is emitting noise, or typically babble noise, speech-like noise. And many of these studies quantify the speech situation by measuring the speech reception threshold, which means that this noise is held at a constant level, and the level of the target, the speech, the useful signal, is varied until one reaches 50% perception. And it does indeed turn out, it has been shown in many studies, that if we have anechoic conditions, so only direct sound here, then it is much easier to understand the speech if those two are separated in space. Other studies have added reverberation, so a room here, but it's still slightly different from the situation we are interested in, because they always have an interferer which has a direct sound and reverberation, and the target, the decided signal, which has a direct sound and reverberation. I will show another example from the literature which shows exactly this classical so-called binaural benefit measured in decibels. And that shows the advantage with having the decided signal and the disturbing signal separated in space. And maybe this is well known, but we can get a maximum of 11 decibels advantage if we move the noise from the source of the useful signal to 90 degrees out. So this all seems to suggest that there are quite a substantial influence or importance of the binaural listening. But if we look at this a little bit more, it seems to be there's one factor or aspect which seems to suggest that this effect is much, much less prominent. And the reason is that we have reverberation in a room which is split up into a good and a bad part. The direct sound is arriving from here typically. The early part, the good part, is like the early part of the reverberation, so it's arriving from all directions. The late part, the bad sound, is arriving from all directions. If we could imagine a hypothetical situation, that if we could somehow magically create a situation where there's no early reflection, there's no early energy, we have only the direct sound and the bad sound, late reverberation. It would be very bad if all the reverberation would come from the same direction as the direct sound, because there would be, the two ears could not separate those two. This would be much, much better if the disturbing signal arrived from the side, and this is probably at least better than that situation. And we could imagine that this does actually correspond to monaural listening if all of these arrived from the same direction. That would be like putting a microphone in a room and listening to those two components. Whereas listening to those two components would correspond to recording with the dummy head or listening with our own heads. And this would be should be clearly better than that. That seems to suggest that we could need to take binaural aspects into account. But then we have those pesky early reflections, and they seem to make things more complicated. So I just pointed out that it seems like our binaural hearing would prefer this situation instead of that, binaural instead of monaural. But for the early reflection, our hearing would prefer this rather than that. So our binaural hearing, since our binaural hearing has to live with both the early and the late part, which has similar spatial distribution, it seems like the binaural hearing cannot really use the full advantage. And I can mention that we were very surprised. It was Ulrich Reiter and we worked on this, and we were very surprised because we just wanted to confirm what we took for granted, and that is that if we put the loudspeaker in a reverberant room, we played speech, we recorded with a dummy head, and then listened to the recording with the two channels kept, and then we switched to mono to give the left signal to both ears. And I would have told any student asking me, saying that this would give a big advantage if we listen binaurally. But when we listened to it, we could hardly hear any difference when it came to speech intelligibility. And that's when we also tried to do recordings and listening tests. We could hardly get any differences. So it seems like all of those that have developed the monaural speech parameters, they have perhaps known or realized that the binaural effect is probably relatively small or very small for listening to speech. So it seems like an extension of the speech transmission index to a binaural measure is probably not going to make a big difference. And before rounding this off and opening for questions, or more questions, let's see. Yeah, so to do this extension is not going to make a big difference, but yeah, we try to round this off then by some quite general points or conclusions here. A first thing, which the first part of the talk was about, was that this two-room situation creates new types of impulse responses that we need to work a bit more with and need to learn a bit more so that we can add recommended values for the type of room called video conferencing room, because they are missing in most recommendations and room acoustics books. In a related, as a related example, there didn't used to be recommendations for reverberation time for arenas for rock concerts. There are different classical music, theaters, etc. But for rock music, they have finally, the last few years, thanks to some work done in Denmark, on the European scene at least, that there are recommendations, studies of the influence of reverberation time, which has, for instance, suggested that the reverberation time really needs to be quite low, between 100 and 150 hertz. So we need to add the video conference room to these classical cases. The reverberation time does admittedly not say everything about room acoustic conditions, but it's there all the time, so we need to start from there and get that right before we start looking into more finer aspects like room geometry and early reflections, possibly. Video conference rooms, like all rooms, should be designed with its use in mind, but often they are treated a little bit less nicely than that, and video conferencing rooms end up in rooms that were available. And the last point was this question about whether we need binaural speech parameters or not. And probably it's going to be a minor improvement. And improvement meaning it's going to predict reality. The improvement in the prediction of reality will be very, very small, I suspect, or quite small, by working out the binaural speech parameter. And that is related to something that can be shown by a curve like this. There are similar curves which show actual speech intelligibility versus speech transmission index. There's a nice relationship, but quite a large scatter, and we are never going to predict reality better than within a certain scatter. And if we are tweaking this model, if we're making the model binaural, I suspect that the improvement in prediction will be increased very, very little, which makes life easier in a way, because we have those monaural measures that we have been using for quite many years. So that is actually, oops, sorry about that. That's, I was going to show the conclusions again, but apparently one has to be careful when stopping here and not driving over the edge. Which I just never mind. Okay, so anyway, thank you very much for listening, and if you have any questions, I'd be happy to discuss.
I'm really surprised to hear that, you know, stereo presentation of reverberation versus, you know, direct signal in front of you is not better than a monaural presentation of reverberation. Does it at least sound like less reverberation? In other words, if I put a finger on one of my ears, this room sounds much more reverberant, but I wouldn't guarantee that I have any higher intelligibility when I don't do that.
No. So I think that's a good point, because it clearly sounds different. If we listen to a mono recording of a room, it sounds very different than a binaural recording. But the speech intelligibility, if you listen for that, I think you will find that it doesn't change. It changes much, much less than you expect from the difference in spaciousness. And for music, spaciousness is a very pleasant part of the impression, but for speech, it's much less so. It might, well, having said that, there's an interesting aspect that maybe you would get more fatigued if you're listening through mono than binaurally. But speech intelligibility is maybe not affected, or possibly not affected.
There have been some hearing aids that have been aimed at stripping away sounds that don't come from the look direction. So if you look straight across the table at a noisy restaurant, you get a non-linear suppression of everything coming from another direction.
Yeah.
And those also do not appear to improve intelligibility. You do improve the apparent signal-to-noise ratio, but the artifacts of all this churning, non-linearly stripped out stuff combined to, it just doesn't help intelligibility scores from what I heard, which was informal. I wasn't supposed to be even told about it. But,
Okay. Yeah. So if these hearing aids, if we are listening in a room with less reverberation, it clearly is better. But then it's done naturally.
yeah.
So with good sound quality. If we try to impose processing, then it is a fragile thing, the speech that we are trying to improve.
And at WASPA, the hearing aid community, as of the last time I was there, was the people that I was talking to were saying that the really best signal processing for intelligibility of speech is the human brain. And so the best hearing aid really is going to present the signal at the optimum listening level, the optimum comfort level across the band, and just let the brain take it from there. Don't introduce artifacts, don't try to strip something out yourself, let the brain do it. Just give it the right level, the optimal level. And does that fit your experience today? This seems a little like a give up to me.
Well, what should we say about that? It's since we don't really notice any difference in intelligibility when we make those changes,
Yeah,
then
the scores.
yeah.
Isn't there something we can do? I mean, some
What?
kind of Wiener filter. I mean, if you know it's noise and you take it out, shouldn't that help? I mean, I guess the brain can do it too. I guess that's the bottom line. Is that we can do externally, the brain can do it.
Yes, absolutely. It's absolutely a great idea to remove the noise, but now I have to be careful again. Step carefully now. Yeah, this thing that when we are doing it by just trying to suppress reverberation, since part of the reverberation is actually a good guy, then we are losing out there. And that will probably affect any kind of clever processing we do something with, which is based on reverberation. We could certainly look further into the details here and find out that there must be situations where this balance is such that this tends to be higher than that. Then it definitely doesn't help to improve this or suppress that. If this one is weaker and that one is stronger, then maybe there should be a net benefit. If we suppress the bad guy, even if we suppress the good guy a little bit, the net effect might be positive. So one has to, but I think it's, so to say, a bit sobering that maybe it's not just about suppressing reverberation, because part of the reverberation is our friend. And what is interesting with John Bradley's studies is that throughout these examples, I have used C50, 50 milliseconds as the division between good and bad sound. John Bradley used 80, and he has even shown a diagram where they varied this time division to find the best match against speech intelligibility. And I think he found the maximum at 95 milliseconds, which means that quite much of the reverberation is really our friend, useful.
On that point, I wonder if it's because the early reflections are more distinct echoes rather than the diffuse late field. I mean, does this time cutoff, is that just a proxy for the more intelligible early reflections as compared to the more noisy diffuse field?
I think that the early reflections are useful is because their contribution are not ruining the modulation in speech. So even if whether the early energy consists of distinct reflections or diffuse sound, I think it's the same effect.
Perhaps if you saw like a correlation with your room size and intelligibility, you know, if your room got bigger and you were checking to see where that cutoff point was, if that cutoff point got longer and longer as your room got bigger, then you might be able to make that argument. If it stayed the same, then maybe it's something more psychoacoustic rather than actual acoustic.
Instead of having it in milliseconds, we should have it in room traversals.
Yeah.
How many wall-to-wall traversals do we define to be the early reflection cutoff?
No, but it's related to the speech signal, to the source signal.
If we're talking about the reverberation, early reflections being at 50 or 85 or 95
Yeah.
milliseconds, how does that translate? I mean, if the room is 10 feet wide, then that's like, 5, 8, or 9 room traversals.
Yeah.
So,
Yeah, so within this could consist of, if we are in a huge room, this could consist of 0 reflections or 1 reflection or more and more, the smaller the room is.
in the big hall, it'd be like a floor bounce, direct and floor bounce.
Yeah, but that we would see if we quantify the early to late ratio. It doesn't matter if this is 1 reflection or 10 reflections or diffuse sound. What matters is the total energy.
Yeah, what matters for what? The total energy determines what?
What matters, the total energy, is what matters for speech intelligibility. Because the energy here is contributing together with, it's close enough in time to contribute constructively to the direct sound for speech, unless we have a very fast speaker.
So you don't want to have more than one phoneme per 100 milliseconds.
Yeah.
Yeah, but I don't know about the speed, but we have studied this with music. And where the type of a reflection really affects. If the early reflections are diffusing, people don't like it. It needs to be specular reflection,
Yeah.
then people like it. If you have highly specular reflection from your side, that's what people like.
And do you remember, that's Tapio's work?
Yes.
Yeah. And do you remember if that is that because the specular reflection gives slightly higher level, slightly more energy, or is there some other aspect? Because it's a question that you could ask me, and I wish I could say it right off the top of my head, but I can't. But I will reveal what the question is, and that is, if we have a wall, one flat, smooth wall, and one rough, source, receiver, here we get a distinct specular reflection, here we get diffuse reflection. If neither of those walls absorbs energy, energy is preserved somehow, but what is the energy level for this, for what is picked up here versus there? There will be a smearing in time by this wall. But is it as simple as that energy is preserved, so the level must be the same? Or does this time smearing have any important effect?
I think it's psychoacoustic phenomenon how in the ear and brains integrate the sound and how the modulation goes. I have no clear image on this, but I think it's quite complicated because
Yeah.
These results you were referencing, were they on music performance basis?
yes.
I think that's a very different situation. Because I perceive an environment like this one very different from a concert hall, for example. So I would think that also preferences in terms of room acoustic program depend on the purpose of the room and also on the performance, whether it's a person talking or an orchestra playing.
Yeah, that's good.
And for music, the spatial aspect is indeed an important factor, which it isn't directly for speech. But still, I think that this aspect of whether it's more tiring to listen to a mono recording, that's an interesting aspect. But that seems to be related to to the use of crosstalk introduction filter when listening to headphones. We can argue that when we want to listen to a stereo recording over headphones, we should reintroduce crosstalk because the stereo was developed for loudspeaker listening. But I think that all attempts to do that are generally less preferred than straightforward listening.
I can cite one publication, which I was not involved in. So they tested preference of listeners of stereo signals played directly to the ears versus like virtual speakers with HRTS and stuff in between. So they kind of found a way to crossfade in between, and they found that something in between the two extremes was preferred. It was kind of similar to playing the stereo signals directly into the ear. Hang on, how was it? I think it was something related to the low frequency boost that direct listening seems to evoke compared to listening to speakers.
Okay.
So it was closer to playing the signals directly than playing them through speakers actually.
So a virtual speaker that's really good.
Sorry?
A virtual speaker that's good.
I mean, it's a different, like also conditioning of the listeners. All those participants there, of course, they grew up with listening. They know what to expect when they're wearing headphones. And probably this has also an influence. If you have people who have spent their lives listening to virtual stereo, whenever they wore headphones, they might have different preference.
Yeah, so some examples that I have heard of such crosstalk introduction filters, you hear artifacts and you are very sensitive to the processing, I think. But as you pointed out, a good virtual loudspeaker is probably the best.
No, because you have to wear headphones.
An even better virtual loudspeaker without headphones.
So you need the virtual speaker and the crosstalk cancellation system that Chris is developing. So that you don't need to wear headphones.
And head tracking, so you can move around.
Doesn't sound like a give up to me so far.
Yeah, so any other questions?
Peter, could you go back to the
Non-specular?
No, back in the decay.
The non-exponential. Yeah.
Just look at that graph again.
This one?
Right. So this implies that there's actually an increase in energy.
Yeah.
And can you explain why?
Let's should do a little bit of MATLABing and try to, we can generate. So IR, I will generate an exponential impulse response without the direct sound, 44,100 we like. We use 1 second room volume just to get the scaling, and distance, let's see, I think the format is such that, there, plot IR. Yeah, so this is an impulse response without direct sound, just the exponential part. And then we convolve it with itself. IR conv equals con2, my own FFT based convolution. And if we zoom in here, I think we can see this growing. Because I think that we can realize it by zooming in even more, that the first value is just a multiplication of two sample values. The second value is a sum of sample 1 multiplied by number 2 plus, so it's a sum of two multiplications. The third value is a sum of etc. So we get more and more interaction, but at the same time the amplitudes of these is decreasing. So after a while that decreasing amplitude takes over.
That's a very unusual physical property. I mean, we don't see that terribly in musical instruments.
But every time you are listening to recorded music in a room, you're probably experiencing this.
And musical instruments, they rarely have coupled.
Yeah. Yeah, I mean, there are things like passive nonlinearities and gongs and so on, where you get the nonlinear effect is this sort of gradual increase of frequencies that then goes back down. But as far as energy,
Isn't that this gong type that the loudest part of the sound of which occurs like half a second after, which is like.
right? Well, certainly the frequencies grow, but I'm not sure. I can't remember if the entire amplitude curve like this would grow.
Let's see, if we listen to first one impulse response.
Maybe the instruments are just small because the sound is very very
too
quickly.
fast. Yeah, this is the more.
So that's just one impulse response. And then the convolved one.
Plus impulse response of this group.
Very good point, Lauri.
And notice that it is twice as long. So in other words, you can involve an impulse response with itself, it gets twice as long. So there's time for it to grow and then come down and still have the same energy when you add the squares. Go ahead. I was just predicting that it'll be twice as long. Maybe it won't be. We'll see.
We are convolving a finite impulse response with an infinite one.
Oh, I thought you were convolving it with itself.
Yeah, but then it's convolved, as Lauri pointed out, it's convolved with this room.
Yeah.
So we get three. IR conv times 100, perhaps. Oh.
Gets kind of metallic, doesn't it? Yeah. Jonathan Abel does this on purpose for reverberation. They'll do, he has this thing called motor reverb, where you take the individual resonances, you map them down to DC and convolve them with themselves a number of times, maybe do some stomp box distortion effects, and then put the modes back where they came from, or somewhere else if you want to have fun. And you get this sort of sparsification of the modes that sounds more ringy like that.
Now we should do this one more version of this, and that is not to convolve it with itself. That might create some artifacts.
Yeah.
We take another one. Even though I don't think those artifacts, they disappear in all the cross convolution, I think. But anyway.
So you're going to pick a different set of random numbers for the...
Yeah. And then IR conv 2 equals there. Sound, and then we do the one, the original one. Oh,
That's better.
that's better.
metallic artifact.
Yeah. Interesting.
People use this trick also in the chant vocal technique. So, an LPC speech is kind of buzzy because you have an impulse into a parallel, formant filter bank resonator. And so every period of the speech synthesis or voice synthesis has this strict exponential decay. It really pops on and comes down. And so if you take the formant filters and convolve them with themselves, then they get this T, e to the minus T kind of thing. And you can approximate the chant technique that way. And it sounds better. It reduces the skirts of the band passes in the frequency domain, which is thought to be part of why it sounds better. It makes the resonances less peaky, and it makes the time domain less peaky. The vocal tract impulse response looks more graceful than just popping on and exponentially decaying and sounding so buzzy.
Yes, same effect is here probably. But I guess it's not so strange that the spectral quality changes, because if we have this impulse response and we take a Fourier transform, the magnitude will certainly, it has this kind of stochastic variation of the peaks, but if we convolve this with itself, it's multiplying this by itself. So every sharp peak will be blown up. And if we do it again and again, that reminds me about that recording.
I'm sitting in a room.
Yes, 100 times or 1,000 times or whatever.
Right.
So, but these, what we get when we generate an impulse response like that is these are not corresponding to resonance frequencies that we measure in a room. These are the stochastic interference peaks that Schroeder derived. And the huge difference is that if we make measurements in a room, different places, and we plot many frequency responses on top of each other, we will see the resonance frequencies in the room on top of each other with different amplitudes. But when we come above the Schroeder frequency, they are all stochastic peaks. And here we get only stochastic peaks. But still, we can probably not hear the difference between a stochastic peak and a resonance, a true resonance. Because it sounds a bit resonating, doesn't it?
Maybe the resonance peak persists longer in time than just stochastic one.
Yeah.
Or maybe just don't hear it.
In this room,
Yeah. I would have guessed that because if we take such a noise sequence and convolve with another one, I would claim that we cannot detect any decaying frequency peak. But it sounds very much like it, like we do.
Well, the peaks that are being accentuated don't have to be just one resonance. They can be, a cluster of resonances that just happen to pile up, and they'll still go up higher relative to the lower peaks as they get squared and cubed. And so it doesn't have to be just one resonance.
No. And if one analyzes what this looks like, maybe it behaves exactly like a resonance, like a pole.
Yeah, it's a stochastic combination of peaks, but it's still a peak. And psychoacoustically, we don't really necessarily know that it's just 20 resonances instead of one. So, yeah, at the shorter frequency, it's something like 3 peaks per critical band or something like that. There's some crossover there.
Yeah.
And then at higher frequencies, it's way, way more. So it's just many, many resonances per critical band of hearing, and we don't resolve it at all.
No.
But there is a lot of resolution of texture within a critical band. There was a study by Andrew Gurzo at Georgetown, is that his name? Studying how many sine waves can you discriminate in a critical band. How many sine waves do you have to add up in a critical band before it sounds like white noise and it's indistinguishable from the noise in the band? It turns out to be thousands of sine waves. So you can hear a lot of detail. There are a lot of difference alignments in texture. It's not just the energy in a critical band we hear. There's a lot of texture that we can distinguish.
Yeah. I was going to say that you can add those 1,000 sine waves in many different ways, but
Bases.
yeah, but that is maybe just reflecting exactly that we can extract that information. Our hearing can extract that there is a difference between this realization and that one.
Yeah, I need to find the study, but I think the acid test is if you have randomized phase and random amplitudes, then that to me is however many of those you can distinguish, that's a strong indicator of our resolution power within a critical band, I would think. So, I have a student who has that paper. I'll ask him for a copy and take a look, hopefully before you leave.
Yeah, please. Okay. No other question? Then thanks again for coming.